Hello everybody, this is the first video of the last chapter from this course. The chapter is called Chapter 13. Uh, so why is it called Chapter 13? We haven't gone through 13 chapters in the class, but it's because it covers Chapter 13 of the textbook. And this chapter introduces the policy gradient approach for the solution of Markov decision problems with the reinforcement learning methodology. So what's the difference between this approach? We called it the policy gradient approach, and other previous approaches seen earlier in the previous chapters. Methods proposed in the previous chapters, they relied on estimating the value function to determine good policies. Okay, so to perform the optimization of a policy, we relied on estimating the value function, and the action value function, and this action value function indicated which actions were good and in which states, and this allowed us deriving the optimal policy. Okay, so this family of methods that we've seen in earlier chapters is referred to the action value methods. Now, in this chapter, we'll do something different, which is to directly learn the policy without relying on an estimate of the value function. Okay, so how we're going to do that, we're going to assume that the policy is a parametric function of the state variables of the problem, and then we're going to learn the parameters of the policy to optimize that policy. So this contains similar ideas to what we did in Chapter 9, in the sense that in Chapter 9 we had a parametric representation of the value function, whereas here we're still going to have a parametric representation, but the representation will be for the policy directly instead of a parametric representation of the value function. So we say we don't rely on an estimation of the value function to try to optimize the policy, but it's possible, if we want, to also include an estimate of the value function within the algorithm we're going to present in this chapter. So we can still, even though it's not required, methods in this chapter which directly learn the shape of the optimal policy can at the same time provide an estimate of the value function, and this estimate can be used to refine the algorithm, the main algorithm proposed in this chapter. But it's not mandatory. Okay, so we can proceed without learning a value function at all. So here we are going to introduce a parameter vector theta, which is in R d prime. So d prime denotes the dimension of the parameter theta, and I use d prime here instead of d because d was used in previous chapters to represent the dimension of parameters of the weights of the value function. So when we're going to talk about parameters of the policy, we're going to use d prime to represent its dimension. Okay, so d is parameters of the value function, d prime is parameters, the dimension of the parameter vector of the policy. So we will write the following. We will write denote pi a bar s theta being the probability of selecting action A, given that the current state is S and the current parameters of the policy is theta. So here we see that the policy pi becomes a parametric function of theta. Okay. Moreover, we said that the algorithm presented in this chapter doesn't necessarily rely on a value function, but it can include an estimate of the value function to refine its performance. So in that specific case, for the refined version of the algorithm, we're still going to denote by v hat dot w the state value function estimate when the current value of parameters is w. Okay, so we can still use an estimate of the value function if we wish to include in the algorithm we're going to present, and here w will be d-dimensional. Okay, so theta is d prime dimensional, w is d-dimensional, d and d prime can be different. Okay, so let's assume that we're trying to find the policy parameters theta so as to optimize a performance metric. Okay, so here the performance metric, or the objective function we're going to consider, is denoted by j. So we're trying to maximize over all possible values of theta the function j of theta. Okay, so here, what is j of theta? Well, if we want to make a parallel with what we've done in previous chapters, j of theta can typically be the value associated with a state as 0. Okay, so let's say we start in a state as 0 and we want to find the policy which maximizes the expected sum of discounted rewards if we start in state as 0. Okay, so this is the typical case. For the remainder of this chapter and specific examples, we're going to only consider this case. However, in practice, in the literature, there are other objective functions that can be considered. Okay, so here when we consider the value function as the objective function, it means we consider expected rewards, but in finance, for example, I'm more a finance guy, so I can talk a bit about this. In finance, we're not only interested in expected value of rewards, but also in their risk. Okay, so we can incorporate risk measures instead of the expectation within J. Okay, so J can be more general than the expected value of all future discounted rewards, but for the sake of this course, we're going to stick with the traditional objective function, which is the value function being the sum of expected discounted rewards if we start in state as 0. So the objective is to find the parameter vector theta, which leads to the best possible policy in terms of maximizing our objective function, which is in many cases the value function. So again, we could consider a stochastic gradient ascent method to do that. So if we wanted to apply a stochastic gradient ascent, we would have the following update rule, theta t plus 1. So our next estimate of parameters is the previous one plus the learning rate times the gradient of the objective function evaluated at the current parameter. So okay, this looks nice, but as we doubt, the story is not over here, because in practice this gradient, it would be if we wanted to use raw calculations, it would be most likely impossible to calculate in many cases. Okay, so we don't know the value function, so its partial derivative with respect to parameters of the policy, well, would be for most practical problems, it would be impossible to get. Okay, so we need to find another way around this. So this particular update rule, it's not feasible in practice. So the methods which, well, we said that the previous method is not directly practicable, but methods that do use these ideas of trying to use stochastic gradient methods to progressively refine the policy itself without relying on the value function. These are known as policy gradient methods. Okay, so gradient, it's because we do a stochastic gradient, but policy gradient because the parameters refined or learned are those of the policy, not the value function. Okay, so we said earlier that sometimes in more refined versions of the algorithm, we can also consider somewhere an estimate of the value function, which will help us. So for we will see these will be used for the assessment of the value of an action. Okay, and when we do include an estimate of the value function within our scheme, then these approaches will be known as actor-critic methods. Okay, so we'll describe the details later on, but if you read a bit about machine learning methods, you might encounter this term actor-critic methods. So these are basically policy methods where we learn the policy, but we still use somewhere an estimate of the value function to assess the quality or the value of the various actions taken by the policy that is being learned. So for this set of slides, we're only going to consider episodic tasks that are undiscounted. So we'll consider no discount factors. But if you want to learn more about the general case, so if you want to consider undiscounted tasks, continuing tasks that are potentially, most likely discounted, then please refer to the textbook for a discussion of these. Okay, but we won't have time to tackle the continuing tasks. Okay, so one might be wondering, well, we have the possibility of learning a value function to get the optimal policy, or we have the possibility of directly learning a policy. Okay, and just for you to know, some researchers or some practitioners, there's a large class of people focusing on one and a large cluster of people focusing on the other. Okay, so both approaches can be very valid in practice, but now the question is, in what circumstances should we use one instead of the other? And this depends on the complexity both of the policy and the value function. Okay, so for example, for some problems, the shape of the value function might be very complicated, but the structure of the optimal policy might be more simple. So in that case, most likely it's more simple to learn directly the policy rather than the complex value function. Conversely, for some problems, the value function shape might be simpler than the shape of the policy. So in that case, if the value function is simpler, well, it might be better to learn the value function to infer the optimal policy. Okay, so it really depends on which one we think is more complicated. Is it the policy or the value function? And for some problems we don't know, so it's possible to try both approaches, and some might work better than the other. Okay, so for some problems we have a good feeling of what should work better, but for many problems we don't know, and it's just a matter of trying them. Okay, so for example, in finance, in my own personal research, along with my collaborators, I've considered mainly policy methods, but some researchers are focused more extensively on learning the value function. Okay. Another advantage of directly learning the policy rather than learning the value function is the starting point. Okay, so when we do these stochastic gradient descent, we typically need to specify a starting point for the parameters. So sometimes for the value function, it's really hard to get an idea of what's the value function and the initial state. Okay, sometimes you have no clue about that, whereas it's sometimes easier to get a better idea of what the optimal policy should look like. So you don't know exactly how it is, but you might have a rough idea of what it should look like. So in that case, it might be easier to propose a decent, not optimal of course, but decent starting point for parameters of the policy. Okay, so if you're teaching a robot how to walk? Well, basically, you know that when both legs are on the ground, it makes sense to raise one leg, and if one leg is up, then you should you should put it down before raising the other leg. Okay, so you have these ideas about the policy that you can incorporate in your initial parameters. So sometimes, for this reason, it can be another argument why, another reason why the policy learning the policy directly might be more easy. Okay, so in this chapter we'll make assumptions about the policy, which is basically that policies are non-deterministic. Okay, so we're gonna presume that policies always entail continuous exploration, which is that the probability of selecting any action in any state, regardless of what the parameters are, these probabilities are between 0 and 1, which means that the policy cannot be deterministic. Okay, it cannot be, these probabilities cannot be exactly 0 or cannot be exactly 1. However, although they're not exactly 0 or 1, we're gonna see that well, we're not necessarily going to see that, but they can become arbitrarily close to 0 and 1. Okay, so although you don't have deterministic policies in that case, you could converge to one such deterministic policy, which would be the optimal policy. The other assumption that we will make is differentiability with respect to theta. Okay, so we're going to assume that we can differentiate that function pi with respect to theta, and the reason why we do that is we want the gradient of this policy pi to exist. Okay, so if the gradient does not exist, then methods of this chapter won't be applicable. Okay, so there exists a typical way. It's not the only possible way, of course, but a very natural way of designing a policy which matches the previous assumptions is the following. Okay, so we can define a parametric function h, which represents the numerical preference associated with an action A in a state S if the policy parameters are theta. Okay, so here the higher h sa theta is, the highest preference you assign to action A in state S when your policy is theta. Okay, and we must assume that that function h must be differentiable with respect to theta. And once we have this function h, then we can apply a softmax normalization function to ensure that probabilities are bounded between 0 and 1. So here, this the probability of selecting action A in state S with parameters theta, we can define it as the exponential of that action preference divided by the exponential of the sum of all possible actions of preferences of all such actions B. Okay, so having this normalization, it ensures that this probability is strictly greater than 0 and strictly smaller than 1. And furthermore, if h is differentiable, because the exponential is also differentiable, then this ensures that these probabilities are differentiable and their gradient exists. Okay, so this is very natural. And if this rings a bell, you might think, hey, I've seen this somewhere. Where did I see this? Well, it's because recall that in chapter 2 we had the bandit the bandit problem, and at the end of the chapter there was an action preference method. And recall that we said this action preference method for bandits, it doesn't rely on the estimated value of the states. It directly relies on some action preference that are learned. Well, it's because the method here we're proposing is a particular case, a more general case than the bandit. Okay, the bandit problem is a particular case of what we're proposing in this chapter. Okay, so the action preference for bandit is an example of policy learning where we didn't use the value function or the estimated value of states. We only used, we directly learned the policy, okay, through learning parameters of this softmax normalized action preferences. Okay, so the in a nutshell, the action preference approach for the bandits is a particular case of what we do in chapter 13. But chapter 13 makes it more general to apply not only to the bandits, which had IID rewards, but to a general Markov decision process where the rewards are dependent and the sequence of states is also dependent. Okay, so now one thing you might ask yourself is, okay, action preferences H, how do we specify these in practice? Again, there are many possibilities, but a very popular choice would be to use linear features. So once again, we can define features or characteristics associated with the various state action pairs of our problem, and we can assume that the action preference for a state action pair is a linear combination of the features of that state action pair, where the weights of the linear combination are the parameters theta. Okay, so this of course ensures that H is differentiable because the gradient is the vector of feature X itself. Okay, so this is a very natural way to do this. Another way to do this, which is becoming increasingly popular in practice nowadays, this is one of the, like, okay, a lot of, let's say, many people are doing this nowadays within the reinforcement learning community. It is to use H, to set H as being an artificial neural network. Okay, so H could be a neural network and theta could be the weights of the neural network. So if we go back one slide, then if you have neural networks with linear outputs, then you can apply a last softmax operation to ensure that your output of the normalized networks are between 0 and 1. So this is very common in the neural network literature to use this softmax linearization at the end, normalization at the end to ensure your outputs are bounded between 0 and 1 and sum to 1. Okay, so this is something I forgot to say, is when we use this softmax normalization, not only actions are bounded between 0 and 1, but when you sum their probabilities across all actions, it's guaranteed to sum to 1. So this is very important if you want to have a valid distribution for the probabilities of selecting all actions A in the state S. Okay, so as we said, action preferences can be typically linear combinations of features of the various state action pairs, or H can be a neural network. And as we've discussed in the previous chapter, or maybe you've seen that in the supplemental material, for neural networks, the gradient of the output with respect to parameters is can be obtained through an algorithm called backpropagation. Okay, so this is, if you use regular packages handling neural networks, there should be a function which provides you the gradient with respect to the parameters through backprop. Backprop is a short name for backpropagation algorithm. Okay, so as we mentioned earlier, when we use such action preference softmax policy, the policy cannot be deterministic, but it can become arbitrarily close to it. Okay, so the probability of selecting the various actions, they cannot be exactly 1, but they can be as close to 1 as they want. So although we don't have the optimal policy at any point in time, if it's deterministic, we might converge asymptotically to it. Note also, so this I haven't discussed uh, much this point. So in except in the bandits case, we have assumed in all remaining chapters that transition probabilities are fixed through time. Okay, so as we learned, the optimal policy is for a fixed set of transition probabilities. The environment doesn't evolve. However, in many problems in practice, the environment does evolve and the problem is non-stationary. Okay, so for example, if you repeatedly play chess against somebody else, that person, not only you will learn from that person, but that person will learn from you, and transition probabilities might be different because the other person might be learning to play against you. So in these kinds of circumstances, the optimal policy might not be deterministic. Okay, so for example, if you play poker, sometimes it's better to bluff. So if you always do the same action in a given set of circumstances, then the opponent should learn that from you and eventually be able to beat you in these circumstances. Okay, so sometimes when the environment adapts to you, and you're in an adversarial setting, for example, it might be optimal to behave randomly in some states to prevent your opponent discovering what you want to do. So in these cases, the optimal policy might be stochastic. Okay, so this is another reason why sometimes considering non-deterministic policies might make sense. Okay, so when the transition probabilities are fixed through time, the optimal there should always exist like a deterministic optimal policy. But when you're in an adversarial setting or a game setting where the opponent learns from you, then sometimes you could have a non-deterministic optimal policies that aren't deterministic. And in these cases, finding the optimal stochastic policies, it wouldn't be straightforward with regular action value methods. Whereas here, when we have policy learning, policy gradient methods, for example, you directly have a stochastic policy. Okay, so you don't have to say, for example, I'm going to behave in an epsilon greedy manner. No, the policy is directly being specified as stochastic. So this solves the problem for these cases where you would want a stochastic policy. Okay. Furthermore, we said that the policies should be differentiable with respect to theta, so that, and this implies that when we move theta a little bit, then the policies also vary a little bit. You don't have very drastic changes of policies. So this might be another advantage with respect to learning the value function, because when we learn the value function, or approximations of the value function, such as in chapter 9. Let's say we use an epsilon greedy approach. When we move parameters just a little bit, sometimes the greedy action might change. So if you move the parameters a little bit, before it was action 0 that was the best, but now we've changed the parameters. It's now action 1 that is the greedy action. So in that case, if you apply policy improvement, even though the value function parameters change just a little bit, then the greedy actions suddenly drastically change, which would have the effect of drastically changing the value function associated with your new policy. Okay, so although your estimate of the value function might not change a little bit, the true value function associated with your newer policy might change a lot. Okay, so the behavior can be quite erratic in that of the policy and the value function in that later case. Whereas when we have policies that vary smoothly due to the differentiability with respect to theta, then you might have less erratic behavior. And for such reason, the textbook states that there are stronger convergence guarantees that are typically available for methods analogous to policy gradients instead of methods approximating the value function. Okay, so again, all these convergence questions, we won't do a formal investigation of them. This might require a very advanced tools of probability. But it's important to let you know that so you have an idea of what are the theoretical underpinnings behind your methods. Okay, so it's easier and you have stronger guarantees of convergence typically for policy gradient methods than for methods approximating the value function with a parametric approximation, for instance, seen in previous chapters. Okay, so as we said earlier, we're going to specialize now to this specific case where we assume that the value function we're trying to optimize is the value function in the initial state, which means that we're trying to maximize across all possible policies, or in fact all possible policy vector parameters, the expected value of the sum of all future discounted rewards. So one thing we have to notice here is that when we change theta, what are we altering here? Okay, so first, when we change theta, we alter the policy directly. So for a given set of states, we are going to change the likelihood of selecting the various actions in these states. But this indirectly impacts also the transition probabilities, because we recall that transition probabilities from a state S to a state S prime is the sum of all actions over all actions of the transition probability to S prime from a state action pair SA times the probability of selecting action A given state S according to our policy. Okay, but if we change theta, this part changes also, so it also changes transition probabilities. So not only do we change the actions we take, but we also change the likelihood of encountering the various states in a given episode. So due to this twofold impact of changing theta, calculating the gradient of the objective function does not seem straightforward. Okay, so this we mentioned that at the beginning of the chapter. If we really wanted to calculate this gradient exactly, that would be probably too complicated for most problems. However, the policy gradient theorem, which is provided in the textbook, helps us about this issue. Okay, so here the proof, I won't provide it here in the slides, but please refer to the gray text box on page 325 of the textbook for explanations about this. Okay, so please go there to read the proof. But I'll provide the result here. The result says that the gradient of the objective function, when the objective function is the value function in state 0, is proportional to the sum across all states of the probability of being in this state according to the on-policy distribution. Okay, so this sum here, we see it in fact represents an expectation under the on-policy distribution of the sum of all actions of this is the Q function, so it's the action value function of the current policy evaluated in state S and action A times the gradient of the probability of selecting action A given we're in state S and given current parameters are theta. Okay, so here this sign here means proportional. It's not exactly equal to that, but it's that up to some scaling constant. Okay, so and here mu, recall it's the on policy distribution. If you forgot about that, please go back to chapter 9 to remember what it represents. But in a nutshell, it's basically the long-term proportion of time you spend in the various states S. Okay. So why is this useful? It's because we can notice that this gradient in the previous expression does not depend on the derivative of the on policy distribution with respect to theta. Okay, so when we calculate a value function, you might think, okay, well, this depends on probabilities of being in the various states. So when we differentiate this, we probably have to differentiate mu with respect to something else. But such derivatives would be extremely hard to compute in practice. Okay, so but luckily here, if we go back one slide, in this expression on the right hand side, there's no derivative of mu with respect to theta. There's only a mu here. Okay, so we won't have to differentiate mu, and this is a much welcome result, because if we had to differentiate mu, then this would be very painful and probably it wouldn't work in practice. Okay, but the first great news is this gradient of the objective function involves the on policy distribution, but we don't have to differentiate that on policy distribution. Okay, one quick note here, the constant of proportionality in the previous theorem is the average length of an episode. Okay, so it's great to know that just as informative purposes, but we won't need it in algorithms shown later on. Okay. Okay. So we said that the gradient of the objective function doesn't depend on derivatives of mu j, but it still depends on mu j. Okay, so and mu j, as we said, mu j itself is very hard to calculate for large problems. Okay, so in practice, trying to estimate mu j for very large problems is not realistic. So we like to have a method which doesn't rely on the calculation of this distribution. So to tackle this issue, we're going to proceed exactly as we did in chapter 9, and we're going to instead of sampling or considering all states weighted by their probabilities, we're just going to sample episodes and take states as they come, because we know their proportion over the long term should match the distribution mu. Okay, so to tackle the presence of mu, we're going to use ideas that are quite similar to what we've done in chapter 9. Okay, so for this purpose, we're first going to introduce a bit of notation. So that might have been introduced in chapter 9, but we're going to use it here, so I'll introduce it here. So we're going to define b tilde it as being t tilde it minus 1 plus 1. Okay, so first, let's go slower. It is the episode, the index of the episode for action t. Okay, so for time step t. So if in time step t we're in the third episode, because recall we said we stack all the episodes one at the end of the other in these algorithms. So if at, let's say, time 8 we're in the third episode, then it I8 will be equal to 3, which means that in the 8th time point, we're in the third episode. So b tilde will represent the time of the beginning of this episode, and t tilde will represent the time of the end of the current episode. Okay, so what this equation says is that the time at which the next episode begins so episodes I begins, is the time at which episodes I minus 1 ends plus 1. Okay, so if you end one episode at the time t, then the next episode will start at t plus 1. Okay, so this is consistent with what we said earlier, that we stack episodes one at the end of the other. So if one episode finishes at this time point, then the next episode will start at the next time point. Okay, so in a nutshell, this says that if we're at time t, the current episode covers the following time points: bit plus 1 until tit, where we have tildes here. And the tildes, if you refer back to the notation, and I think it was in chapter 6 or 7, I'm not sure exactly, probably chapter 6, it's because here these are cumulative. So for example, t without a tilde, it's just the length of a given episode. But when you sum the length of the various episodes to get to your current episode, then you had to incorporate tildes. So here we can define tau I being a random time in episode I, which has the following probability distribution. Okay, so the probability that tau I is equal to j is 1 over, this is the number of time steps within an episode, the time at which it ends minus the time at which it begins plus 1, and for any j between b till I and t till I. Okay, so basically this tau I has a random time within all time points of episode I. Okay, so here tau it is simply a random time across the current episode in which time t is. Okay, so if we're in time t, then time t spans the episode in which time t is spans a given set of times, and tau it just takes a random time among all these times for the current episode in which time t falls. Okay, so one quick remark here why we introduce this is because the distribution mu is the distribution of S tau it. Okay, so S tau it, it's basically the state associated with a random point in time in an episode. So it can be shown that the distribution mu, the long-term percentage of time in the various states, is simply the distribution of some state taken randomly at any time point within an episode. Now I've written C exercises. I just realized I haven't provided the solution for this, so hopefully I will have time to do this, but otherwise I just give you the result here and I'll leave it up to you to try to show this. Okay, but I will try to provide the solution by the end of the semester. So let's go back to our previous result, which we call, we called it the policy gradient theorem. So here, this is our policy gradient theorem, and this, according to what we just discussed here, because mu s is the distribution of a state taken at any random time within the episode, then this expression can be expressed as the expectation under the current policy pi. Okay, because here maybe I should have made this more clear, but this mu here is associated with a given policy. So if you change the policy, you change that mu, but here mu is the distribution of the state when we have for the current policy. So maybe I should have written mu of theta to show it depends on the policy. Okay, but this expression is the expectation under the on-policy distribution for policy pi of this guy here, so the sum across all actions of the value function in a state that is random, whose time is randomly chosen within an episode, times the gradient of the action A within that state with respect to policy parameters. Okay. So this is good. This allows to express the gradient of the objective function in a different way, and we'll continue discussing this guy. Okay, so here, so what we can do, instead of considering this gradient in a regular gradient ascent, we could do stochastic gradient ascent. Okay, so instead of considering the gradient, we could have an unbiased estimate of the gradient to perform the adjustment of parameters. So instead of considering this whole guy, we could simply consider the value within the expectation to make our update. Okay, so if we only consider what's inside the expectation, well, it's an unbiased estimate of the gradient because when we take its expectation, it gives the gradient itself. Okay, so we, instead of the gradient, we can take what's inside the expectation to obtain a stochastic gradient ascent instead of a gradient ascent. So this would entail that this stochastic gradient ascent would be replaced, this regular gradient ascent would be replaced by the following stochastic gradient ascent, where we replace the gradient by what was inside of the expectation. Okay, and notice here, this is a randomly sampled time, but when we go through all the stages or all the time steps among the episode, on average, the time will be the randomly selected within an episode. So the frequency will face the various states st among episodes will match the on policy distribution because the frequency will face the various states. It's just the long-term percentage spent in each state asymptotically. So we can replace s tau by st because s tau the s tau and st, when we let t go through episodes continuously, then they will have the same frequency. Okay, so this gives us the following stochastic gradient ascent. Already we have something nicer here. Okay, so we don't have the on policy distribution nowhere here, so already we see that we're getting something more convenient to work with. Okay, so this is called an all action method. So why do we call it all actions? It's because there's this summation over all possible actions. But in practice, if the action space is too large, so if you have, let's say, 1,000 actions in a given state, then you might not want to sum this across all actions. It might take too much time or be too inconvenient, especially if for some actions you don't have very good estimates. So we will continue refining this all actions stochastic gradient ascent to circumvent the need to sum over all actions. Okay, so how will we do that? So we can notice that our gradient, so this is what we've shown in the previous slides, the gradient of the objective function with respect to parameters is the expected value when the state follows the on policy distribution for policy pi theta of the sum across all actions of the action value function in state S and action theta times the gradient of the policy for action or the probability of selecting action A given the current state and current parameter vector. Okay, so how do we go from here to here? Well, here we simply multiply at the numerator by pi and divide at the numerator by pi here. Okay, so we multiply both at the numerator and the denominator by the probability of selecting action A given the current state. And here, how do we go from here to here? Here it's because it's going to be easier to see it in the opposite direction. Okay, so if we start here, how to go here is because instead of summing across all actions, we can randomly take an action from the current policy, And if we randomly take an action, then the average, so when we take the expected value across all such possible actions, then the expected value across all possible actions will simply be the sum of all actions times their associated probability. Okay, so instead of summing across all actions summing across all actions and considering this quantity weighted by their respective probabilities, we could instead simply randomly select an action based on the current policy. Okay, so here we have this term here, which we can plug here. Maybe I'll highlight this. We have this here that we can plug here, but here we replace action small a, the deterministic value, by a randomly selecting action. Okay, so the gradient here is proportional to this quantity, which is the Q function for a state in action at a random time, times the gradient of the probability of action A divided by the probability of action A itself. Okay, so now let's take the third line and do a copy paste. So copy, and we paste it here. So now how do we go from here to here? Well, we notice that the Q function, the state action value function, the action value function, is the expected value of the return given we are in state S, S tau it, and given we take the current action A tau it. Okay, so we can replace the Q function by the conditional expectation of the return. Okay, so this equivalence is something we've shown in chapter 3 most likely, or maybe chapter 4, but this is material we've covered already. And what we see here, we said that in the algorithms for this chapter, we don't want to rely on estimates of the value function. But here, what we had early here, this is an estimate of the value function. Okay, so what we wanted here is to circumvent the need to estimate that. But now that we replace that by the expectation of the return, we see that this value function vanished. Okay, and here this is the double expectation theorem. So when you have the expectation of a conditional expectation here, okay, before double expectation theorem, we notice that when we condition over action A tau it and state S tau it, these quantities, they become constant. Okay, so again, it's easier to see how to go from the third line to the second line. So in the third line here, when these quantities are inside the conditional expectation, because we condition with respect to these action A and state S, they can be treated as a constant because we kind of fix them when we condition with respect to them. So because this is the case, because we can treat them as constant, we can take these out of the conditional expectation and get to this what we have here. Okay, so we can, if we're in the third line, we can take this guy and put them out of the conditional expectation because we condition on action A and state S, so we can get to here. Okay, so to go from here to here, it's easier to see it in the opposite direction from here to here. Okay, so for those who did more advanced probabilities, it's simply because action A and S are measurable with respect to the sigma algebra generated by these, so we can obtain this. And once we're in the third line, then it's simply a double expectation. So the unconditional expectation of a conditional expectation is simply the unconditional expectation itself. So this is the expectation over the on-policy distribution of the return at a given random time within the episode times the gradient of the policy of the current action divided by the probability of the current action characterized by the policy divided by the probability of the action A at the current time. current, and when I say current time, it's the time randomly picked within an episode. Okay, so here what we've obtained, if we recall what we had earlier we had that J theta was proportional to this. Okay, so this is the derivation we just obtained. Okay. So here we just showed that the gradient of our objective function is proportional to the expectation under the on-policy distribution of this. The return times the gradient of the probability of the current action divided by that probability. So if we want to apply stochastic gradient ascent, instead of considering the expectation, which is the gradient, we can replace the gradient by what's inside the expectation, because what's inside the expectation is an unbiased estimate of the gradient. Why unbiased? Well, when we take its expectation, it's the gradient itself. So we can proceed as follows, that if we do a stochastic gradient ascent, then the next value of parameters is the current value plus the learning rate times what's inside the expectation times the return in state t times the gradient of probability of action at divided by that probability. And here, how to go from 2 to 3 is because when we take the derivative of the log, okay, so just recall that, maybe I'll write that. So if we have log of f of x, and if we differentiate this, then this is just 1 over f of x times f prime of x. Okay, so this is how we get from the third line to the second line, because when we differentiate the log, it's the gradient of what's inside the log divided by the function. Okay, so here, this is how we obtain the third update rule, and this update rule is called reinforce. So this is called the reinforce algorithm. And here we have something that we can use. Okay, so if you look at the structure of this equation, what do we need to obtain parameters? We need returns. Okay, so returns. Okay, so here we see this is a Monte Carlo type of algorithm because this involves the returns for the entire period, okay, until the end of the episode. And here, so this, we can obtain it if we simulate our system or if we interact with our environment. And here what's in there, this is the log we know that, of the probability of selecting the various actions with respect to the policy, and this, we have that also. Okay, so in practice, if we select pi being a neural network, or pi being for example, the softmax of softmax weighting of the action preferences, which could be represented as linear combinations of features of states, then the gradient of the log, we know this also. So in this formula, we know every single quantity, so that this algorithm is applicable in practice. Okay. Conversely to the true gradient ascent we had earlier, where we either rely on knowing mu or knowing the value function itself, which was not applicable in practice. But now this reinforce algorithm, this update rule, can be applied. Okay, so as we said in the previous reinforce algorithm, we have the return, which appears in the equation. Okay, so it's a Monte Carlo algorithm. So unfortunately for this algorithm, the update can only be performed once GT is observed, which means at the end of the episode. So again, in practice, when episodes are very long, you might not necessarily want to wait for the end of the episode to start updating your parameters. You might want to do faster learning. Okay, so we will generalize this shortly. Okay, but before, let's notice the following. Under the reinforced algorithm, the update, so the variation of our parameters, is the product of three terms: the return, the gradient of the probability of selecting the current action in the current state, and 1 over the probability of selecting the action in the current state. Okay, so here in what follows, we will provide an interpretation of the algorithm. So here we give the formula. This formula here we provide it, but it's just math calculation that led to it. So next we will try to give a formal explanation or interpretation of why this works. Okay, but we realize here, as we said, that the difference between this and this, it's the product between three terms, well, up to the learning rate constant, but it's the product of GT, the gradient, and 1 over the probability of action A. Okay, so how does it work intuitively? Well, intuitively it can be seen as follows. So let's do a bit of recall of what the gradient is. The gradient is the direction in which if the parameters move in that direction, you would increase the probability of selecting action A the fastest in state ST. Okay, so let's go back here. This gradient here, it gives you the direction such that if you move the parameters in that direction, then you will have the fastest increase of selecting that action A in state S. So, because, so basically, let's go back here. Basically, what this says is we're going to move the parameters. We're always going to move the parameters in the direction to increase the probability of selecting the action we just did select. Okay, so whenever we do an action, we always, in a given state, we always increase its probability. Okay, this might seem weird, but let's explain that. So here we increase the probability, but the amount in which this is increased, it's weighted by these two quantities, GT and pi. So why is that the case? Because the update is proportional to GT, the highest or the higher the return is, the bigger update we will make. Okay, this makes sense because if we have a super large return associated with that action, then it means that this action might be very worthy, so we should increase its probability a lot. Conversely, if we have a low return for associated with that action, the action will not be very worthy, so what the algorithm proposes is to increase it, but just slightly. Okay, so you might think, well, why increase it? Why not decrease it? Well, this will come back to this shortly. Okay, but for now, for actions which have a very high return, we're going to increase their probability by a lot. And for actions which have a very low return, we're going to increase their probability, but just by a lot. Okay, so just one quick remark here, because the probability of the various actions in a given state S must sum to 1. When we increase the probability of some action, the probability of the at least many other actions must decrease so that their sum still sums to 1. Okay. Okay, so proportionality to GT, I think it's pretty clear why this appears in the previous algorithm. It's because we want to increase more the probabilities associated to actions which lead to a higher return. Okay, but now why this weighting factor 1 over the probability of selecting action A? Okay, this is because when you go through episodes, every time you face an action A, you increase its probability. Okay, but if for the current policy, your probability of selecting an action A1 instead of an action A2 is twice as likely, then because you face action A1 twice as many times as action 2, you will increase its value twice as many times. So this is unfair for action 2 because the increase in action 2 would be smaller, not because it gives poorer results in terms of returns, but just because you don't pick action 2 often. Okay, so this would be unfair. So to make this more fair and to have a more common ground for all actions, we're going to inversely weight by the probability or frequency in which we face the various actions. Okay, so if we face an action twice as many times than another, we're going to divide their update size by 2, so as both because one is updated twice as much. If we have half the size of updates, then it gives fairer ground where you don't penalize actions that have a very high return, but who are encountered very infrequently. Okay, so this is the idea why we have this 1 over pi factor within the reinforced algorithm. Okay, so this all makes sense. The update here is proportional to the gradient. So the gradient tells you that you're going to move parameters in the direction which increase the likelihood of selecting the current action A you've selected in the current state. But you want to increase to make the update of parameters larger if you had a larger return, because you want to, for actions that were deemed worthy, you want to move parameters further in that direction to increase the probability of that action more. But you scale with respect to pi at the denominator because you don't want to penalize actions that are selected infrequently. You just the only reason why you would penalize an action is if it gives poor returns, not because it's sampled infrequently. Okay, so this is the interpretation of the reinforced algorithm. Okay, so reinforce, as we saw earlier, it's a stochastic gradient method. Okay, and we discussed earlier in this course, although we didn't go through formal proofs, we mentioned often that stochastic gradient descents or ascents have good theoretical properties, and you can often have assurance of convergence to a local minimum under standard conditions over the learning rate. So if you suitably shrink the magnitude of the learning rate through time to meet conditions outlined in chapter 2, for instance, then you can guarantee convergence to a local optimum. Okay, but again, all these convergence proofs are out of scope of the current course. But the drawback is that although you have theoretical asymptotic convergence, you might be wondering, well, what happens before infinity? So for a finite number of episodes, what happens? And because it's a Monte Carlo method, the target, this involves GT, which is the return observed only at the end of the episode, then this method can have very high variance in practice. Okay, because the return, it's the sum of all discounted rewards, And because you have many rewards, there's a lot of variability in the return. So because it's very variable, the reinforced algorithm, although it converges asymptotically, over the short term, it might vary or fluctuate wildly, which slows the learning. Okay, so we need to discuss methods which could provide potentially help us with reducing the variance or variability of the reinforced algorithm. Okay, so I'll stop the video here because it's probably already been an hour, but I'll do the other video in a way that you can really listen to them one at the end of the other. Okay, so I'll assume you can stop the video here and start the other one in 1 second, and there won't be a very conceptual cut between both.